When an officer issues a command on a modern vessel, they interact with an interface layer, far removed from the physical machinery turning below deck. The primary inputs on this console dictate how the ship steers and powers itself, relying on three specific mode selections: Aziman, Cruise, and Fast Steering. Selecting the incorrect mode during alongside maneuvering poses a severe safety hazard, threatening both the vessel and the surrounding port infrastructure. These buttons do not pull mechanical cables, physically actuate hydraulic valves, or throttle fuel. They submit a request. The true authority over the vessel's movement resides in the AC-110 propulsion controller, a master logic cabinet standing between the bridge's request and physical plant. The AC-110 intercepts every command. It identifies which operational mode is currently active, calculates the safety parameters of that specific mode, and applies strict automated physical envelopes to the propulsion hardware. This intermediate automation layer exists to ensure that human error at the helm cannot inadvertently tear the ship apart under hydrodynamic stress or destroy harbor infrastructure with a massive power surge. Understanding exactly how the AC-110 calculates and enforces these operating envelopes marks the dividing line between a basic component operator and a principal marine engineer. Before analyzing software limits, engineers identify the hardware fallback, the Azipod room, situated directly above the submerged unit. This compartment houses the raw mechanics: hydraulic steering gear, slewing wheel, and winch motors. Adjacent is the AIU, housing ASU-36XD servo controls and override levers. If the bridge's remote control network fails or the AC-110 logic crashes, all operational command safely routes to this specific room. Engineers in the Azipod room physically bypass the AC-110, using the local interface to directly actuate steering hydraulics and manipulate propeller RPM. The control hierarchy is absolute. A local hydraulic or electronic override initiated here strictly supersedes any command sent from the bridge. Automation logic manages the ship's routine transit, but the Azipod room provides the mechanisms for direct manual control of the propulsion plant. When that vessel approaches a harbor, the operating environment shifts to tight, high-risk confines near concrete berths and assisting tugs. To navigate this space safely, the bridge selects Aziman, which stands for Azimuthing Maneuver Mode. This top-down schematic shows Aziman in action. The system enables absolute directional freedom, authorizing the pod to rotate a continuous 360 degrees, vectoring thrust in any direction. This is mechanically enabled by the fluid swivel module, maintaining unbroken hydraulic and data channels during endless rotation. Infinite rotation introduces a critical danger. If the pod is aimed sideways toward a berth, a sudden surge of full nominal power would generate extreme propellant wash, destroying tugs, docks, and nearby structures. To prevent this, the AC-110 applies an automated safeguard. This chart tracks allowable power. In Aziman, the system permanently caps maximum propeller power output below the physical limit. Even if an officer slams the helm to 100%, expecting immediate power, regardless of the operator's intent, the automation system categorically denies that full power request. This restriction is hard-coded safety logic, deeply embedded in the system. The operator cannot manually overwrite it from the bridge console. Aziman intentionally trades power for absolute freedom of vector geometry, strictly to protect external infrastructure. Moving out of the harbor, the vessel transitions to high-speed transit in the open ocean. Here, the bridge selects Cruise Mode, or Open Sea Mode, which applies an operational envelope that is the exact inverse of Aziman. Cruise Mode enforces a strict hardware restriction. The steering angle is firmly capped at exactly 35 degrees port and starboard. Hydrodynamic physics dictate this limit. Turning a massive pod fully sideways at high transit speeds generates catastrophic lateral roll forces against the hull. By locking the steering angle, the system prevents the vessel from unintentionally capsizing itself due to a drastic pilot error at the helm. Because tight maneuvering is no longer required in open water, the trade-off is clear. The previous Aziman power restriction is completely lifted. Returning to our power chart, the output ceiling breaks entirely. The cycloconverter is now authorized to deliver 100% of nominal propeller power upon request. What the bridge loses in rotational freedom, it has gained in raw forward transit thrust.
Cruise mode guarantees structural survival by sacrificing extreme maneuverability to safely unleash maximum power. The propulsion logic system is a rigid, unyielding matrix of automated rules, not a series of fluid suggestions. Bridge buttons do not control the Azipod directly. They select one of these inescapable operational envelopes. AZ mode grants unlimited vectoring while limiting power to protect the harbor. Cruise mode grants maximum power while limiting vectoring to protect the ship's hull. And the Azipod room serves as the final physical override when all remote logic fails. Knowing these absolute boundaries separates a technician pushing buttons from an engineer who fully understands system limits. Mastering these automated envelopes forms the foundation of marine electrical and operational command. Next time, we decode fast steering gear mode and map the critical feedback loop differences between follow-up and non-follow-up control.